Hi everybody, welcome back. This is Matrix video number 3, and I'm here to talk to you a little bit about how to figure out the determinant for an n by n upper triangular matrix. So remember, we said that this is simply the multiplication in the diagonal, and the same thing applies for lower triangular and a diagonal matrix. So we're going to prove today the case for the upper triangular. There are two ways to go about this. So there's the way that you just hop right into it, or induction. And in induction, you consider a base case. So our base case would be a 2 by 2 matrix. Show that it holds for that, and assume that it holds for an n by n matrix. And then using that information, we show that it holds for the n plus 1 by n plus 1 case. So we're going to do it the first way, and just do it. So normally in the previous videos, we'd calculate the determinant by, say, looking at this element, crossing off the row and the column. And in this video, we are going to consider a different element. So instead of considering this element and crossing off that row and column, we're actually going to consider this element and cross off that row and column. Because we notice that this whole entire thing over here is consistent of zeros, so everything just cancels and we're left with this simple one term. So that's how we're going to go about this. And remember, the determinant of a matrix M, det M, is just equal to the bars. So this is equal to M11, again that's a bar, times M22, M23, all the way over to M2n. And then we have zeros going all the way down, M33 all the way over to M3n, and that's down to MNN. And again, that's 0 here, 0 there, all that stuff. So we see, hey, there's only one term left. So if we do this again, we get M11, M22, crossing off that row and column, remember, we're going to get M33 all the way over to M3n, and this is down to 0 again, and down to MNN. So if we do this one more time, we can see that this pattern is just going to repeat. So we get M11, M22, M33, and this is going to be, of course, M44 all the way over to M4n, down to MNN, and again, these are zeros. So we see that this is going to be M11, M22, M33, MNN. Or, maybe a better way to put it is the product of I equaling 1 to n of M, I. So that looks like M11, M22, M33, all the way to MNN. So that is exactly what we said the determinant should be, is the product of everything on the diagonal. So that was just a simple proof of how that works. Of course, we didn't consider like every single one, because you can't consider infinite going down, but we just saw a pattern. So I want to talk about one more thing that you might find useful, so hopefully that proof made sense. For the diagonal case, that's just really easy. So if you had a matrix M that looks like A, B, C, D, E, all the way down to like Z, let's say, zeros here, zeros there, you're just going to see that when you take the determinant, you're going to get something that's A, B, zeros, C, D, zeros, zeros, all the way down to Z. And that's just going to repeat, so you're going to get A, B, C, all the way down to Z. So it's just an even simpler case to consider. So what I want to talk about next is if you have a matrix that looks like M is equal to M11. And remember, it's the row and then the column, so it's going to be M12 all the way over to M1n, down to MNN, and this is going to be down to MN1, all the way over, this is M22, etc. So the trace of a matrix is defined as the sum of the elements on the diagonal So what does this look like? For our matrix above, if we just take the sum of all of those elements, we're going to use that sort of same indexing before. So the abbreviation is TR of M, and we're going to use the sum from I equals 1 to n, because it's an n by n matrix. And these elements are just MII. So this looks like M11 plus M22 all the way up to MNN. Hopefully that makes sense. So the trace of a matrix is just that. The trace of a matrix is not multiplying things on the diagonal, it's the sum of the elements on the diagonal. And finally, one last thing I want to talk about that I didn't mention for matrices. So, in our matrix multiplication world, we mentioned one thing earlier. So if we have a matrix A commutes with the identity, of course, and the identity times that matrix just returns that matrix back. Now you're probably wondering, do matrices commute? And the answer is not all. So some of them commute, like you can see the identity commutes, but in general matrices do not commute. So if you have two matrices A and B, AB is not necessarily equal to BA. I mean, they very well could be equal, but you can't assume that they commute. So now in terms of our operator land, the way we think about this is to calculate the commutator. So for example, the commutator of A and B is equal to AB minus BA, which is equal to 0 if they commute. So let's take a look at an example for that then. Alright, so let's consider our last example then. So if we wanted to figure out if, for example, SY and SX commuted, we'd do stuff with the commutator. So first off, we start by writing out what the commutator of SX and SY is. Okay, so we have SX hat, SY hat is equal to SX SY minus SY SX. And you might remember that SX is equal to H bar over 2. And then in the matrix we have 0, 1, 1, 0. And then SY looks like H bar over 2. 0 minus I, 0. Alright. So let's take a look at this then. So we get SY, SX, and SX, SY. So we're going to consider the first term first, SX, SY. So we get H bar squared over 2 squared. So I kept it as 2 squared because we're going to notice something. So the matrix 0, 1, 1, 0 times the matrix 0 minus I, 0. So this is going to give us H bar squared over 2 squared. And then for the first term in here, in case you don't remember your multiplication, that term is going to be this row times this column. So that gives us I in this spot then. So for the next spot, we're going to get 0. For down below, we're going to get 0. And then in the spot on the right, it's going to be minus I. Okay, now we're going to pull out an I and we're going to realize some really clever things. So we have I H bar squared over 2 squared times the matrix that is 1, 0, 0 minus 1. And since you all are geniuses, you remember that this is a spin matrix as well. So H bar over 2 times 1, 0, 0 minus 1 is SZ. So this is equal to IH bar divided by 2 SZ. Okay? So now we need to figure out the other direction, the SY, SX. And then we can finally determine if the commutator is non-zero. So SY, SX is equal to H bar squared over 2 squared 0 minus I is 0, and this is going to be multiplied by 1, 0, or 0, 1, 1, 0. So this gives us h bar squared over 2 squared. And again, in the first spot, it's going to be minus I. And then we have in our second spot that it's going to be 0. And then down below, we have 0 and then I. So if we pull out a minus I, we have minus I h bar squared over 2 squared. That's a terrible h bar. 1, 0, 0, minus 1. So yeah, exactly. You all remember that that's the SZ matrix. So this is I h bar divided by 2 SZ. So now we're going to put together all the information that we know. So the commutator that we were considering in this problem was SXSY, which is SX, SY, minus SY, SX. So this is IH bar divided by 2, SZ, minus a minus IH bar divided by 2, SC. Okay? So this is just IH bar SC. So what did we actually conclude with the commutator? Take a couple seconds to yourself and think like, what does it mean when the commutator is non-zero? And you got it! Or I just blew your eardrums out because you had your earbuds in really loud, and that was your mistake. So, we found that the commutator between SX and SY is non-zero. In other words, it's equal to IH bar SC. So this implies that SX and SY don't commute, right? Because the commutator is non-zero. So whenever you're trying to determine if two elements commute, you're trying to show their commutator is non-zero. So for example, or 0 if they commute. So for example, if you're given, I don't know, like X and P, for example, if you're given matrices corresponding to those, do X and P commute? No, they do not. Because that's one of our fundamental commutators. I'll say that we learned that it's IH bar. So, we would see that commutator is non-zero because they don't commute. So this is generally a good strategy to use if two operators don't commute. So hopefully you learned a lot in this video. We proved about how an upper triangular matrix has the determinant that's just multiplying the elements on the trace. We learned about a trace. So if we calculate the trace of a matrix, we're just adding together the elements on the diagonal. So remember, you have to be really careful. The trace is adding that. But if we're looking at finding that determinant, you're multiplying the things on the diagonal. So just be careful with your verbiage there. Some people might say you multiply the things on the trace. So be careful about that verbiage. We also learned about multiplying two operators together, the SX, SY, and SY, SX, to determine the commutator. Sometimes it might be useful to, like for example, you could act on alpha or beta, where alpha is the spin up column vector and beta is the spin down column vector. And we could have also figured out that strategy. So again, thanks for watching. Hope you have a great day, and don't forget to be awesome. Thanks. Bye.